Hello everyone. In this video, we're discussing two very important concepts of skeletal muscle physiology. First of all, muscle twitch, and second, muscle tension. And here are the specific learning objectives for this video. So basically, so far we've looked at what happens inside of a muscle cell, but we haven't really described how these cellular events actually help us create a meaningful contraction. So that's the question that this video is attempting to answer. To understand how we can create and control muscle contraction, think about, for instance, holding a pen to write, throwing a ball, or moving a heavy piece of furniture, we first need to understand what a muscle twitch is. In a nutshell, a muscle twitch represents one stimulation, so one action potential, in one muscle fiber. So it's very, very small. So when the one muscle fiber receives the input of only one action potential, what we see is one single contraction relaxation cycle. And we can see that in the bottom graph here. So in this graph, we have muscle tension on the y-axis and time on the x-axis. So muscle twitch would be a single contraction and relaxation cycle. So the contraction we see here, where tension increases, and then the relaxation we see here, where tension decreases. But before this contraction and relaxation can occur, there's another period that comes before that, which we call the latent period. And we see it right here. The definition of the latent period is the delay between the action potential in the muscle fiber and the start of the tension development. So let's look at it in the graph here. The second graph here shows the action potential within the muscle fiber. So you see here the characteristic shape of the action potential. But what I want us to focus on is the timing between the start of the action potential and the start of the contraction. And I've indicated this with the green line here. So the green line indicates when the muscle fiber first becomes depolarized. So that's the start of the action potential inside the muscle fiber. And when you line up the start of that action potential with what's happening in the muscle, you can see that there is a time here indicated between the green line and the purple line where no tension is developed. And that's what we call the latent period. Now going back up one panel, what we see in the top panel here is the action potential in the motor neuron. So remember, here we're looking at action potential in the muscle fiber. At the top, we're looking at the action potential in the motor neuron. So with our knowledge so far, we know that the motor neuron action potential occurs just slightly before the muscle fiber action potential. And then this muscle fiber action potential occurs just a tiny bit before the start of the contraction. So my question to you is, which events take place inside the muscle cell during each of the muscle twitch phases? So think back about our previous knowledge. Inside the cell, what happens during the latent phase? Inside the cell, what happens during the contraction phase? And what happens during the relaxation phase? That's what we're discussing in the next few slides. So starting with the latent period. By definition, the latent period is that time or that delay between the action potential in the muscle and the start of the contraction. So what happens inside the cell during that latent period? Basically, it allows for all of the events of the excitation-contraction coupling that we've already discussed to take place. So think back of our knowledge of excitation-contraction coupling. What needs to happen between the action potential and the contraction? A few things. First of all, the action potential needs to move or propagate down the T tubules. Then we've talked about the conformational change of the DHPR and the RYR. So conformation change of our two proteins, DHPR and RYR. After that, calcium needs to move out of the sarcoplasmic reticulum. So calcium efflux from the sarcoplasmic reticulum. And finally, we need sometimes for calcium to diffuse through the sarcoplasm and then bind to troponin. So calcium diffusion. So none of those events take a lot of time. However, they are all required for contraction to occur. So this latent period accounts for all of these events to happen before myosin and actin can actually start interacting together. Now moving on to the contraction phase. That's when tension is being created, or that's when tension increases within the muscle fiber. What cellular events explain that? This is when the cross-bridge cycling occurs, and as a result, your sarcomeres shorten. So that's your contraction phase. And finally, we have a relaxation phase, and that's when muscle tension decreases here. And that's due to calcium being actively transported back into the sarcoplasmic reticulum, which causes calcium to unbind from troponin. And as we know, that stops the cross-bridge cycle and the sarcomeres lengthen back to their original position. So if we look back at the twitch as a whole, the latent period, the contraction phase, and the relaxation phase, these concepts aren't new. We've talked previously about all of the cellular events that explain each of these phases. So what's new now is just to make sure that we understand when latent period, contraction period, or relaxation period, each of these events take place. So one twitch is a good start to explain how we create meaningful force. But one twitch is still pretty irrelevant in the amount of force that it can create. It's really, really small. We're talking about one action potential in one muscle fiber. So what actually determines the amount of muscle force that's created? And the short answer is the number of cross bridges. And that's a very important relationship. So I'm going to put a few stars here so we understand how important that is. There is a proportional relationship between the number of cross bridges and the amount of muscle force. And that's what we see here. The higher the number of cross bridges in a muscle, the higher the force is created within that muscle. So if we want to put some numbers to illustrate that, let's say in the entire muscle, you have 1,000 cross bridges. That creates less force than if you had 1,000,000 cross bridges within that same muscle. So that's the first important message here. When we increase the number of cross bridges within the muscle, that increases the force created by that muscle. Now, the follow-up question to that is what determines the number of cross bridges? And that's actually determined by 3 different factors. The resting length of the sarcomeres, temporal summation, and spatial summation. And we're going to discuss all 3 of these factors right now, starting with the resting length of the sarcomeres. So let's look at this cartoon here. On the y-axis, we have tension or force created within the muscle. And on the x-axis, we have the starting position or starting length of the sarcomere. And you can see that there is an optimal length for the sarcomeres here. When the sarcomeres is too short, it cannot create a lot of tension. When the sarcomere is too long, it's the same situation. It cannot create a lot of tension either. But there is a sweet spot between short and long, which is called this optimal resting length, where the sarcomere is able to produce 100% of its maximal force. So why is that? Why is it that a really short sarcomere is inefficient at producing force? And why is it that a very long sarcomere is also inefficient at creating force? So it has to do with the amount of overlap between the thin and the thick filament. So let's start looking at sarcomere C here, which is our optimal position. You can see that the myosin, represented in purple here in the middle, and the actin, in red here, have some amount of overlap, but it's not too much and it's not too little. That allows for cross bridges to happen. In order to create tension, your actin and myosin must interact together. So there must be some overlap. Now let's compare this with the situation in E when the sarcomere starts at a very long length. And what you can see here is that basically myosin and actin do not overlap at all, or the thin and the thick filament do not overlap. The thick filament is right here, the thin filament is right here. If there's no overlap, it is impossible for actin and myosin to form crossbridge because they're too far away from one another. Now let's compare this with our sarcomere A here. So that's when the sarcomere starts in a very short position. And here, the problem is that there's too much overlap. Here's my analogy for you to try to understand this. Let's think of myosin and actin binding together as a handshake between two people. In our situation C here, our optimal situation, the two people that want to shake hands are in front of one another and there's no obstruction between them. So it's pretty easy to shake somebody's hand in that situation. When the sarcomere is too short here, as in situation A, the sarcomere becomes really, really crowded. So there's a lot of proteins that interfere between the actin and the myosin. So going back to our handshake analogy, it's like you want to shake the hand of the person in front of you, but there's 5 or 6 other people between you and that person. So it's much harder to get that handshake connection in that situation. It's the same thing that happens in our sarcomere A. It's just too crowded so that the cross bridges are actually quite inefficient. So here's a summary of what I just said here. Too much overlap, which we see here, render the cross bridges inefficient. And there's also little room or little opportunity for the sarcomeres to shorten. Too little overlap, cross bridges can just not form because there's a lack of proximity between the thin and the thick filament. So our optimal starting position is our situation C here, where all the myosin heads overlap with actin, therefore they have the opportunity to form all these cross bridges. So that's how the resting length of the sarcomeres affects tension production. That's a relationship that we call a tension-length relationship. Moving on now to our second factor, temporal summation. So the concept of temporal summation tells us that the higher the action potential frequency within the muscle, the higher the muscle tension. So when we explain temporal summation, we have to think about a single muscle fiber. So we're not talking about an entire muscle, we're just talking about one muscle cell. So in this slide and the next slide, the graphs are all set up the same way, where we have tension on the y-axis and then time on the x-axis. And each of the black triangles represents one action potential. So our first situation here shows a low action potential frequency, roughly here every 200 milliseconds. And with this low frequency, what happens within the muscle is that it gets stimulated, and we see this contraction phase, and then we see the relaxation phase. But the action potentials are so far apart that there's actually time for the entire relaxation phase to occur. And our tension in the muscle cell is back to 0 before the next action potential takes place. Same thing here. Tension increases, tension decreases, all the way back to 0 before the next action potential. So the maximal amount of tension here that's created with low action potential frequency is relatively low. What typically happens in muscle fibers is that the action potential frequency is greater than that. And that's what we see right here. So we have an action potential at 200 milliseconds, and let's say here another one at 275 milliseconds. So this interval of time here isn't long enough for the fiber to fully relax before it gets stimulated again. So that's what we see here. There's the first stimulation here. Muscle tension increases. It starts to relax, but before it can get to 0, there's another stimulation right here. And up it goes again. From a cellular perspective, think about it as the first action potential released a bit of calcium from the sarcoplasmic reticulum, allowing some cross bridges to form. With the second action potential, there's an additional signal, so even more calcium move out of the sarcoplasmic reticulum, bind to troponin, therefore allowing even more cross bridges to occur, and that's why we see an increase in muscle tension. And if we compare this situation to the first one, you can see that the tension created by the second situation with medium action potential frequency is greater than the one created with low action potential frequency. And that's what we call summation. Another word for summation is addition. So basically the muscle adds the tension created from the second stimulation onto the one that's created by the first stimulation, and that gives us a greater amount of tension. So that's the concept of summation. So let's look at this concept to its maximal effect. So let's now increase the action potential frequency even more. Now you can see how close together these action potentials are. And what happens here is just the concept of summation, but taken a step further. So you can see that with each additional action potential, the tension is added onto the previous one. Summation, summation, summation. To a point where the muscle fiber reaches its maximum tension. At that point, increasing action potential frequency isn't going to increase tension because the muscle has already reached its maximum tension. Think about it as, the muscles already engage or form all of the possible cross bridges in that muscle cell. However, I want to bring your attention here to the dips between each of these stimulations here. That's what we call an unfused tetanus. So tetanus refers to the fact that the muscle fiber achieved its maximal tension, but unfused means that some partial relaxation still occurs, which you can see with each of these dips here. And that's different from our last example, which is what happens with a very, very high frequency of action potential. And we call that a fused tetanus. So once again, tetanus meaning maximal tension is reached, but fused means that the action potential frequency are so high that there is no longer partial relaxation. And that's what you see right here. You see the summation, summation, summation. We reach maximal tension, that's tetanus, but we don't see the dips anymore. It's a flat line of continued maximal tension. That's what we call fuse or complete tetanus. So taking this all back together, temporal summation is really a concept that states that the higher the frequency of action potential within a muscle fiber, the higher muscle tension is achieved. And we've looked at 4 examples of that, starting with low action potential frequency, where full relaxation occurred, moving on to a high action potential frequency where we reach tetanus, but it's an unfused tetanus, and finally, very high action potential frequency where we reach a fused tetanus. The last factor that we're discussing today is spatial summation. So when we talk about spatial summation, we have to introduce the concept of motor units. So by definition, a motor unit is one motor neuron and all of the muscle cells that it innervates. So when we think about spatial summation, now we have to think about the entire muscle, right? When we talked about temporal summation, we talked about it in a single muscle cell. When we talk about spatial summation, we have to think of the entire muscle and all of its cells. Let me draw what motor units look like. So we know that a muscle has many, many, many muscle cells. So each of the cylinders that I'm drawing here represent one muscle cell. And I'm going to make some in different colors here. So this is a sketch of what a muscle could look like. So basically, in black here would be the entire muscle, and within the muscle, we have different muscle cells in different color. Now, each of these muscle cells receive input from a motor neuron. But a motor neuron actually gives input to more than one muscle cell. And that's where the color coding is important here. So here is a motor neuron, and the blue motor neuron will innervate all of the blue muscle cells. We'll have a purple motor neuron, same idea, gives information and action potentials to all of the purple muscle cells. And then same thing with our green motor neuron, which gives information to our green muscle cells. So here what we've drawn is basically 3 motor units. So remember, a motor unit is one motor neuron and all of the muscle fibers that it innervates. In this case, we have a blue motor neuron that innervates all of the blue cells. So that's our first motor unit. That's motor unit 1. We have a second motor unit in purple here, one motor neuron and all of the muscle cells that it innervates, and now we have a third motor unit here in green. Now, motor units can be relatively small or very big, and it depends on the muscles. So if you think of the muscles in your eyes, for instance, that have to do very fine movement, the motor units inside those muscles are very, very small, 3 to 5 muscle cells per motor unit. So basically similar to what we just drew. Now, if you think of your quadriceps, which is important in powerful muscles, and where we don't need the fine control, a motor unit in your quadriceps can have over 1,000 muscle cells in it. Now, even within a muscle, the motor units will have different sizes. So now let's look at the number of cells within each of these motor units. So in the blue motor unit, we have 1, 2, 3, 4, 5 cells. Put that here. In the purple motor unit, we have 1, 2, 3, 4. And in the green motor unit, 1, 2, 3. We have 3 cells. So now remember that we're talking about force production. And even without getting more instruction, you guys probably intuitively know that the larger the motor unit, the greater force it produces. So the blue motor unit here would produce more force than the green motor unit. Because when the blue motor unit is activated, tension will be created in 5 of the cells, right? So more cross bridges will be created. Compared to the green motor unit, when it fires, only 3 muscle cells would form cross bridges. So that would give you less cross bridges and less tension. So here's a summary question for you. Can one somatic motor neuron innervate many muscle cells? Absolutely. They all do, okay? Each motor neuron will go and signal to more than one muscle cell. Now, can one muscle cell receive input from many motor neurons? And the answer is no, okay? Each of the muscle cells that we drew here only receives information from one motor neuron. So let's take this concept a step further. What we're seeing here is very similar to what we just draw in the previous slide. So we have a muscle here with many muscle fibers that are all color-coded. So the pink motor neuron over here innervates all of the pink cells, which are 1, 2, 3, 4, 5, 6, 7. Let's compare this to the red motor neuron that innervates all of the red cells. 1, 2, 3, 4, 5, 6. So there's 6 cells in the third motor unit. Now we know that the purple motor unit will produce larger force than the red motor unit just because it's bigger. However, motor units will always fire in the same order. And that order is always small motor units first, large motor units after. And the reason for that is that the smaller motor units have a lower activation threshold. So you need less of a stimulus in order to activate a small motor unit. So in this case, our red motor unit would be recruited first because the smaller of the two, and our purple motor unit would be recruited after because it's a larger motor unit. And that's what we see right here in just another cartoon. So once again here, that represents your central nervous system. So the stimulus comes from your brain and activates 3 different somatic motor neurons, a purple one, a green one, and a red one. The purple motor unit innervates 3 muscle cells. The green one has 5 muscle cells, and then the red one has 7 muscle cells. Small motor unit, medium motor unit, and large motor unit. Now I want to bring your attention to the graph on the right here. So we see tension on the y-axis with strength of the stimulus on the x-axis. So there's 2 things we can see here. The first one is the order of recruitment. If you look at the x-axis, the first motor unit that starts making tension is our purple one, this one, right? And that matches what we just said. Your small motor units are recruited first because they have a lower activation threshold. So small motor unit first, medium motor unit after, and then large motor unit last. So that's the first concept that we can see here. The second concept that we can see with this graph is the amount of tension that's created. So compare here the amount of tension that's created when the purple motor unit fires with the amount of tension that's created when the red motor unit fires, right? In this case, we have low tension with the purple one because it is a small one, small motor unit. And we have large tension or large force created by our large motor units. So let's put this back all together. What is spatial summation? Spatial summation is a concept that says that the more motor units that are recruited, the greater the tension. And I'll write it down for you here. If you increase the number of motor units recruited, you increase the amount of muscle tension created, or muscle force. So the more motor units, the more muscle force. That's the bottom line. However, there's 2 other concepts here that are important. First, we always recruit our small motor units first. So these are recruited first. And small motor units create weak tensions compared to large motor units, which are recruited last, but create a much larger tension. So here we go, guys. How do we create tension in our muscle? 3 different factors. Our sarcomeres must start in this optimal resting position. We can increase muscle tension by temporal summation. In other words, increasing the frequency of action potentials within the muscle. And we can increase the amount of tension created by recruiting more motor units, a concept that we call spatial summation.